In problem 7, we're given this block. Half of it is made of iron and half of it is made of aluminum. And we're given the dimensions of D1, D2, and D3, and they're asking us to find the center of mass of this block. They also provide us with the densities of iron and aluminum. Let's think about this conceptually at first. If we look at this conceptually, we're going to use symmetry to our advantage. So here's the left side of the block that's made of iron. Here's the right side of the block that is made of aluminum. But because it's a nice rectangular shape, it is symmetrical about the red plane. If I slice this block down the center through the red line there, you see the top half is exactly the same as the bottom half. So it is symmetrical about the red plane. If I slice it down the middle with the blue plane, then the back side is exactly the same as the front side. So it's also symmetrical about the blue plane. And so the center of mass must lie within that slicing plane. So the center of mass must be in the blue plane. It must be in the red plane. And if the left side was the same as the right side, then the center of mass would also lie in the black plane. But it's not. The iron side is more dense. It is heavier than the aluminum side. So that means my center of mass lies in the intersection of the blue plane and the red plane, because it must be in both of those planes. And the green line shows that intersection, and that's the only location that is common to both the red plane and the blue plane. If the black plane also was a plane of symmetry, then we'd be done. The center of mass would be at the intersection of all three of those, and that would be the geometric center. But because the left and the right side are not symmetrical, now we just know that the center of mass lies on this green line. And because we know that the iron side is heavier than the aluminum side, that means the center of mass is going to shift from the geometric center to my left here. It's going to be somewhere over here. How far? Well, that's where the math comes in. So let's take a look at the mathematical solution now. Before I noticed that the book put the origin right here, I chose the origin to be right here. That's going to simplify my solution considerably because I already know that the center of mass is on this green line. So if I choose this to be my origin, then I will just have a coordinate that is, if this is my x-axis, that will be in the negative x direction, and my y value and my z value will be 0. So I'm going to solve it that way first, and then we'll convert our answer to show what you should have gotten had you used the origin to be at this location like the book showed. All right, so I'm going to treat each side as if it is a point mass. So the aluminum side, it's completely symmetrical, just the aluminum portion, so I know its center of mass is right in its geometric center. And same thing for the iron side of the block. It is also uniform density throughout the iron, so the center of mass of the iron section of the block is right in its geometric center. So that's just half of 11 centimeters. So my center of mass for the aluminum is plus 5.5. And my center of mass for my iron section is negative 5.5 on the x-axis. So I'm going to use my equation, 1 over the total mass times the sum of all the collection of the point masses that I'm finding the center of mass between. So there's only 2 of them, the iron side and the aluminum side. And the total mass is density times volume, but I have to add up the density times volume for iron and the density times volume for aluminum. So there you see there the density of iron times its volume plus the density of aluminum times its volume will give me the total mass. And then the mass of each piece, m sub I, is just the density of that section times its volume times its location. Negative 5.5 for the iron and positive 5.5 for the aluminum. You see here, both sides have the same volume. So these 2 volumes cancel with this volume and this volume. And then I just plug in my numbers now, the density of iron and the density of aluminum. and we get negative 2.7 for my x-coordinate. The y-coordinate and the z-coordinate are 0 when I choose this spot to be my origin. So you can see that simplified things a bit, but now let's convert our answer to be here where the book indicates the origin should be. So with a little analysis, so my x-coordinate is back here to the green line. So if D3 was 13 centimeters, that means my x-coordinate is negative 6.5. Let's recall the right-handed coordinate system. The right-handed coordinate system starts with your right hand, of course, and then you start counting with your thumb. 1, 2, 3, x, y, z. So if you do that, 1, 2, 3, x, y, z, this is always the positive x, this is always the positive y, and this is always the positive z. So no matter how you orient it in space, that will always be the relationship between the positive x-axis, the positive y-axis, and the positive z-axis. X, y, z. And if we look at how the coordinate system is shown in the problem, this is how our hand would be oriented, and here's our coordinate system. And then my y distance to the midpoint was 11 centimeters, so I show here that if the center of mass was negative 2.7 from the midpoint, then it's positive 8.3 from the other side of the block. So there's my y-coordinate, 8.3, and then halfway up is half of 2.8, which is my dimension for D2, so that's 1.4 centimeters.